Alright, so for this reaction, what we have here is a, looks like a methanol attached to a cyclohexane, and we're going to be reacting it with an acid and some heat. So what this is called is a dehydration. If you look, you'll notice this this OH up here, and you'll think hydroxide, that's a very strong base, which makes it a terrible leaving group. Since we're going to be dehydrating this this molecule, you'll probably think that we'll be losing a water, which is true. And how we get that water is we deprotonate this acid using this base, and we form a water on this molecule, and then the water is free to leave. Water is a great leaving group. So what we're going to do is, I'm just going to expand this out a little bit. This is bonded to an OH. You know, and we got a bunch of just acid just floating around there. So the mechanism for this is going to look very similar to this. We are going to have this this hydroxide, this base, deprotonate this acid, and then we are going to be left with a positively charged oxygen on this water molecule here, along with a negative HSO4. From here, what's going to happen is this oxygen is going to pull in these electrons, and the water is going to freely leave. Water on a molecule will just freely fall off. Nothing really has to happen to it. So then what this takes us to is what is known as a carbocation intermediate. See, this carbon gave up its electrons to the water, so we have a plus on this carbon, along with an HSO4. 4 is too big. HSO4 plus an H2O. So now, from here, what we're going to look at is how we got to get rid of this carbocation. So there's multiple ways to do this. To get rid of a carbocation, we can either go through an elimination or a substitution. Now, what we know about substitutions is that we need to use nucleophiles, and it has to be a well, never mind. We're not going to go into that. Just it's an elimination for dehydration. So you've got this H here, and what you're actually going to do is you're going to use this newly formed water as your new base, because this is actually going to be a stronger base than your deprotonated sulfuric acid, because sulfuric acid is a strong acid which makes its conjugate base very weak. So what's going to happen is your water here is going to come in and snag this. This is going to move up here, and what we're going to be left with is that right there. Voila! Easy as that. But you may think, that's not the most stable reaction. I'll say you're right. We've got this plus here that will actually, because of a hydride shift, what it'll do is this hydrogen will actually donate to this carbon, and then this positive will move down here. See, yeah, you still see that? I'll draw it right here. You're left with, and then this will be a CH3 and a plus. And then from here, we can actually make a couple different molecules. We can take this and make it become either, you got one, you'll have a charge there, or I was going to say here too, but since I don't have any stereochemistry shown, you can just flip that and it'll do the exact same thing. But how that's going to come about is, again, you have this positive, and you've got two hydrogens sticking off here, and your water is just going to kind of come flop one of these off right here, and you'll be left with and those are your two products from that reaction. Except, I say two products, this is going to be very trace. Because what you've got here is you've got a primary carbocation, those never form. So I think actually most people would say that's even wrong. This right here is the product you're going to be looking at for the dehydration of that with an acid. And again, that's an acid catalyzed dehydration. So we can go through that again real quick if you want. We've got CH2OH. OH is a strong base. It's not going to leave this easily. So what we need to do is we need to have acid that can deprotonate and bond to this OH to make it a good leaving group. It'll make water. The water leaves. We're left with a positive oxygen there. So the oxygen freely, pulls in those electrons, and like I said, water leaves easily, so it's gone. We're left with a carbocation intermediate. It's a primary carbocation. So what it's going to want to do is rearranged for the most stable arrangement. We'll have a hydride shift where the hydrogen is going to jump up to this carbon here, the carbocation, and the carbocation is going to switch down to a tertiary carbon. Tertiary carbon will then have a adjacent carbon's hydrogen removed by the base, which is now water, and then the double bond will be formed, and that will be your product.